Perfect. Hello, everyone, and welcome to the Future Mobility Lab seminar for today, 30th of April, 2024. I'm Simona Mihaita, an associate professor at QGIS. I'm currently working with a lot of passionate people about the combination of transportation science and mobility, incident management, public transport optimization, and so on. Today, as part of our seminar, we have some special guests that I would like to present to you in just 1 second. So let me just share my screen. All right, so the topic that we are going to have the presentation for today is around geospatial data analytics, all sorts of projects that have been undertaken by Ryan Watson Consulting from Melbourne, Australia. And as part of this presentation, we have Richard Watson, born in Melbourne, studying physics at the University of Melbourne with a Master of Science degree with honors from that university, a PhD in nuclear physics from ANU, which is absolutely fantastic. I love the domain of nuclear physics, and I know how challenging it is. So he also worked at as part of the Australian Defence Science and Technology DSTO in Canberra, where he got a graduate diploma in operations research. And I think that while working in there, Richard basically gained an international reputation in information system planning. He basically worked on designing and working for Corania, a small consulting firm in Canberra. After that, moving to Melbourne and working as a senior research scientist for DSO Maritime Operations, and also lecturing in Swinburne University. Ever since, basically, Richard also did seasonal lecturing in software engineering and Java programming at several universities, which is absolutely great. We know how valuable the experience from industry is. And basically, in the last 5 years, is mostly working in the field of Internet of Things, big data analytics, working with local councils, and basically founding the company that we are going to see today and the outcome of that work. If everybody agrees, I can introduce Peter, and then I will let Ryan and I will let Richard and Peter swap between each other during the presentation as you may seem fit. So Peter, also born and educated in Melbourne, earning a Bachelor of Science in Physical and Nuclear Physics from Melbourne University. He also was afterwards in the University of Massachusetts, US, as a postdoctoral research associate, working on nuclear structure using electron scattering, which is absolutely fantastic if you ask me. After returning to Australia, he also worked in DSTO in Melbourne, on applying hydrocores to explosive modeling, and then working as a research scientist. I think that there's quite impressive career pathways, and also really applying all the knowledge to build distribution simulation technology for assisting defense with the training requirements. I think that also, Peter is an Australian delegate for international committees, the ISO, the IEC, JTC, and also working in the last few years together with Richard on their new adventure to basically work with local councils and solve some of the burning issues. I will now stop my screen sharing. Thank you so much, everyone in the room, for joining us today. And I will pass on now to Richard to share his screen and his work.
Okay, thanks, Simona. I'll just share my screen. Can I share my screen? Yes. Okay. All right. As Sandra has said, we're going to be talking about the projects being carried out by our consulting firm, Ryan Watson Consulting. I'll speak for the first half, and then Peter will take over. I'll say a little bit about our company.
Before you start, I think I can't see the slides yet. Is that?
You can't see the slides?
Not yet. From my side, no.
Have you allowed me to view the screen?
Yes, I think so. In the middle of the bottom side, there's a share screen, and you just click on that, and you'll have a screen or any window you open listed, and you just click on which one you want to share.
Yes, if you have multiple screens, usually Zoom wants you to select what number of the screens you would like to share.
Richard, do you want me to share it?
From my side, I always get tricky. I'm always sharing the wrong screen sometimes.
Yeah.
And then
Okay.
swap.
Okay, I'll click on share screen.
Yep.
And you just select.
It should be okay.
Yeah.
Yeah, coming up now. That's right. Good.
Okay, can you see my screen now?
Yes.
Yes.
All good.
All good.
All good. Yep. Let's go.
All right, well, I'll continue with what I was saying. The presentation today will say something about our work and over the last few years. We've only been a company for 3 years, so I'm only going to talk about recent work. Peter and I have been doing research together for a lot longer than that, but I'll concentrate on recent work. I'll say something about geospatial data analytics, which is the main area that we're working in now. I'll talk about a project we've been doing for a few years on Victorian road accident data analysis. Then that work is continuing. We're looking at hotspot prediction for road accidents using machine learning. Then I'll hand over to Peter, and he will talk about a work we're doing on canopy coverage analysis using 2D and 3D data, and a project that Whitehorse City Council have sponsored for us and our interns. Okay, we have done work in these areas since 2020. We've worked in smart parking. These projects haven't actually been sponsored projects, so we didn't get any money out of them, but we sponsored projects done by students, and also we had interns from Swinburne University and Monash University. We did a project on smart waste management, and then another one on sentiment analysis from social media. And then I will talk a bit more detail about the work that we've been doing on road accident analysis. Then Peter will talk on our work on canopy coverage analysis. For those who are not familiar with geospatial data analytics, I just want to say that that involves using geospatial technologies to gather information to give data that can give a deeper understanding of many issues. It's very important in the present time. And this spatial data can answer questions, help with predictions, analysis, and decision-making. So it's a branch of data science that involves geospatial data. Spatial data can be combined with other data from various sources. These are just some of them: weather data, census data, satellite imagery, aerial photography, social media data. And this data can be used in a wide variety of different industries. Some of them are listed here: urban planning, transportation, natural disaster management, healthcare, agriculture. We haven't worked in all these areas by any means, but there's a great scope for using geospatial data in many areas today. it's advanced a lot from what it was a few years ago, where it was just mainly used for map production. Okay, I'm now going to say something about this Victorian road accident project. We've confined our data analysis to Victorian data. Trying to do it for the whole of Australia would have been a bit too much, but we made some good progress. So we analysed these data sets using Python spatial libraries. There's many spatial libraries that can be used. And so we had to learn how to use them. It was a great learning exercise for us. We did various statistical tests to establish spatial autocorrelation and spatial distribution of road accidents, and looked at the spatial factors contributing to road accidents, such as land use, built infrastructure, road characteristics and population density in the vicinity of roads. We found these from open data sets and their connection to the road accidents. More recently, we've been doing work with street view images, road accident sites, and we're still working on this, hoping to include that in a machine learning model of road accident hotspots. This work has been published, basically an introduction to this work, just recently published this year in the Journal of Advances in Information Technology. So if anybody's interested in this, that is the reference. The data sources for this project are federal, state and local open geospatial data. Also other sources like OpenStreetMap and Google Earth for the world. The analysis we did included vector, raster and point cloud data. They're the main data types of geospatial data. Technologies or techniques included spatial join, coordinate projection, and so on. There's much to learn in the field of geospatial data analysis, and basically it was a learning exercise for us. Geospatial statistics, we analysed the data using techniques like kriging, the Moore and I test, kernel density estimation, the Gettys I test, geographically weighted regression. So these are covered in the report that we published. Machine learning, we haven't made very much progress with that yet because there's a lot more data which we need. But some of the Python libraries used for that are sklearn, Keras, SHAP. Visualization is an important part of any data science project. And in the field of spatial data, many types of maps can be produced, Cora paths, heat maps, and so on. I'll just show you a few of those very briefly in a minute. Right, these are just some examples from the data visualization. I'm not trying to cover all the details of this, just to show you some of the types of maps that can be produced. You can see two maps of Victoria, one with the road accident location shown, another with the local government areas and the frequency of road accidents in those areas. There's a map of the Melbourne metropolitan area with showing land use. That was part of what we did. The last two charts are actually the Geelong Central Business District. There's a map showing the locations of the road accidents. There's another map which is a grid which we needed to aggregate the road accident frequencies in a grid. So, okay, so there's just some examples. There are many more. I said that the next stage of this was a road accident hotspot prediction using machine learning. Importance of road accidents and their impacts in order to design safer roads. Contributing factors can be categorised based on characteristics such as road, vehicle, human, speed limit and others. Our work hasn't tried to cover all aspects of contributing factors. The whole field is enormous. We've confined ourselves to geospatial data. So we've left there's hundreds and hundreds of papers being published in the literature, and studies have been done. So it's quite a big field to get into. Machine learning models use accident and geospatial environmental data to predict hotspots. And I mentioned or additive explanation technique for explaining the predictions of machine learning. That's a very important technique. We haven't made very much progress with it, but it's used more and more today. Okay, I'm now moving on to the more current work of looking at the environment of road accidents. A road can be defined in the form of its environment, such as trees, open space, buildings, and identifying the association between the environmental factors and road crashes can be crucial for making roads safe. And the technique, this data science technique of deep learning, which is similar to machine learning, can be used to extract environmental features from street view images and feed these features with other factors that lead to road accidents into the model. The environmental features can be extracted using a technique called semantic image segmentation, or PSPNet, which is a popular architecture. There's other architectures, but we haven't gone into all of them. Segments in these images are obtained using a package called Detectron 2, which was developed by Facebook AI Research, and that implements state-of-the-art object detection algorithms. Segment information can be used for machine learning algorithms and can feed these features into the model. Okay, this chart shows a two-dimensional image, photograph image, applying PSPNet architecture segmentation technique can result in a similar technique to shown there. And this is one paper which describes this technique is found in that reference. It's actually very recent, just late last year, in uncovering the association between crashes and street level built environmental features using street view images. This is a bit more examples of the images of road accident hotspots, I think they are. And that the table there is just some of the results that have been obtained. This work was done by one of our interns, so he's with us today. So if you have any questions about the details there, he might be able to answer if I can't. Okay, I've said there's a lot more to be done. We need to develop a model using deep neural networks. The chart on the right is just a schematic of what a deep neural network model might look at. And limitations in this work are just using street view images. Street view images need to be up to date for being useful for road accident analysis. And redesign roads in developed areas. Yes, if the roads have been redesigned since the street view images were produced, that's not going to be very useful. Okay, well, I'll now stop my screen sharing and hand over the chair to Dr. Peter Ryan, who will continue speaking about our work.
Thank you, Richard.
Yeah, thank you, Richard, and thank you, Simona, for the gracious introduction at the start. That was excellent. So I'll continue on from Richard's presentation. I was also involved in the road accident work. We do work on things together. What I've been mostly working on more recently is canopy coverage analysis using satellite aerial imagery. There's a big push in the Melbourne Metro councils to increase their tree canopy coverage to reduce the urban heat island effect. Can you all hear all right? Is that all right?
We can hear you. We don't have the screen
Good.
shared. If you can.
Oh, really? What have I done there? Oh, yeah, okay. Zoom, screen share that.
I thought I stopped sharing.
No, we can.
That's good. All right.
Oh, boy.
Good. So yes, we've been working on tree canopy coverage. Local councils are trying to increase tree canopy coverage to reduce urban heat island effect. Urban heat island effect can make up to a 4-degree difference by providing shade and a phenomenon called evapotranspiration. So simply by having trees, your council can become cooler. The trees hold the water vapor and then the water vapor evaporates, providing a cooling effect. And of course, they provide shade as well. There is a tendency for new houses to be built with very few trees, and this is causing concern in councils like the area I live in, Melbourne. It's a lot of big houses with no trees, so areas get hot in summer. So you can use 2D and 3D imagery which is collected by remote sensors, and you can use this imagery to analyze changes in canopy coverage over time. Light cloud point data is obtained from 3D scanners that project light at objects and interpret the scattered ray. That's known as lidar. It's an amalgamation of light and radar. It uses light rays rather than radio waves and just scatters off the buildings, ground, etc. And you can then get a 3D image. So Ryan Watson Consulting has been engaged to work with Whitehorse Council in Melbourne to analyse some LiDAR data and some RGB imagery, which we've been given. Let's move to the next slide. Right. So where's Whitehorse? This is the Melbourne metro area. Whitehorse Council's in the purple here. It's Whitehorse Council's offices. And on the left and right, we've got aerial photography showing the topography of Whitehorse, and on the right side we've got just an image showing planning overlays. And they've got a website, of course, there where you can get all these nice images from. The background to the study is the Cooling and Greening website. This is a state government Victoria website which has policy, strategies, resources, and sort of history of all the cooling and greening initiatives that Melbourne is involved with. This is supported by universities, CSIRO, government departments, and also Melbourne Water. The CSIRO are trying to create a high-resolution map that records how urban vegetation across Melbourne has changed between 2014 and 2018. There's always a bit of a delay because it's hard to get recent data. It's quite a complex job to get comprehensive coverage for a large area like Whitehorse. So that can take some time. The Cooling and Greening report showed that canopy cover across Whitehorse was 18%. Unfortunately, this represents a bit of a decrease from 2014 in 4 years, because the strategy is to try and increase tree canopy cover to 27%. So from 18% to 27%, that is a 50% increase. That's a huge change. Beyond 2030, to get to 30% by 2050 would be the long-term plan. Again, another substantial increase. So what project deliverables were to look at the difference between the 2014 and 2018 tree cover and look at the change, measure the tree cover across those 2 years, and then look at the change. We're also going to look at the urban heat and heat vulnerability index, although I think those requirements require infrared imagery, which we haven't got. As you can see here, this is the Melbourne metro area. It shows the tree coverage. Whitehorse is very much in the leafy eastern suburbs, high coverage of trees. The western suburbs are fairly bare. And below here we have I think this is the heat vulnerability index. You can see that because they've got trees, that the eastern suburbs have got lower heat vulnerability indices compared to the western suburbs, which are fairly flat, hot, and have high vulnerability indexes up in the red area. So, right. So the Whitehorse City Council data set, we've been given some of the data from 2018. LiDAR data, collected by aerial imagery. Aircraft flies on this flight path all around the place. That just shows the flight paths, hundreds of laps up and down the council. The final data's got about 100 of these files, each of about 350 megabytes. So it's very, very data intensive. One needs quite a powerful computer to analyze a 350 megabyte file. We've been given more recently some high resolution data from 2023, which has got file size of 1.2 gigabytes. So that's just amazing. The data is much nicer data, actually. How to analyse this data? We had the choice of using ArcGIS, which the council has been using previously. ArcGIS is produced by the Esri organisation, a multinational organisation, perhaps founded in America, but it's multinational, so it's used worldwide. That's a very powerful tool, ArcGIS. It requires a license, which is expensive. An alternative to ArcGIS is QGIS, which is an open source tool. And QGIS is quite good. It has many plugins, has these tools which can read the 3D data called LAS tools, and viewers like JavaScript viewer like QGIS 2.3 GS. So we found QGIS to be quite a good alternative to ArcGIS, which we didn't even try. We just had a quick look at it and decided we couldn't use it because we couldn't use it beyond this project. And QGIS was determined as the appropriate way to move. This picture here shows QGIS user interface with a canopy model, and the red line is simply a line across Whitehorse, and this shows the profile of tree heights. So quite a good tool. QGIS has interesting things. You can literally just drag and drop an image in there, drag it from Explorer and put it into QGIS, and it plots the image. And you can drag and drop other files, Esri shape files, and it graphs them straight away. So that's very useful. And Esri ArcGIS can't do some of those things. So we found it to be quite useful. I've been able to get up to speed with QGIS reasonably quickly, and our interns have done some very good work with QGIS so far. Other ways to analyze trees, you can use packages like Detect Tree. This Detect Tree does not work with lidar data. It works with normal flat RGB data. So it just uses RGB imagery, so you don't need those huge data sets. It uses supervised learning approach where you break the data into a training and testing set, and it works quite well. But I feel it mainly works for small areas like this, and it's not really Detect Tree is not really suitable for a large scale council block, kilometre by kilometres or several kilometres by several kilometres. It's also still a work in progress. I've been helping this guy test it a little bit, I guess, Marty Bosch. And in fact, his latest version doesn't work. I'm waiting to get a new version that does work. So the Detect Tree is good for the aerial imagery for small areas. Richard talked about Detectron. Detectron's more for the ground level images, not aerial imagery, as we think. Again, these are just interesting areas we're following. So we're required to find the canopy height model for Whitehorse. What you need to do is determine the digital surface model and the digital terrain model. The terrain model is the bare earth model, where the height of the bare earth above sea level, I guess. The surface model is the model of the heights of the trees and buildings and other features. If we subtract those two, if we subtract the digital terrain model from the digital surface model, we get a canopy height model looking like this. So that's what we're aiming to do. We actually needed both QGIS and Python to extract this canopy height model. So here's QGIS. We start with a 3D LAS file, point cloud data. You can move that around and show the curves, etc. Show the topography. You can develop. So QGIS extracts all the points and classifies those points as ground, vegetation, buildings, road surface, noise, unclassified and other stuff. And by creating the digital terrain model and digital surface model for that particular tile, we can create a canopy height model like this. So I think the areas are all 1 kilometre by 1 kilometre. That broadly shows the greens parts of the trees in that area of Whitehorse. So we start with the 3D point cloud data file, and we end up with a 2D raster file, which is the canopy height model. It's an XY, two-dimensional XY file. Each point in X meters, Y meters is each point, it represents a height on the graph above the council. We could continue to use QGIS to analyze the canopy, but we found it more convenient to use Python to take those files from QGIS and then read and analyze the output. You can create a basic canopy height model here, just shown here. It's all coloured blue because height is under 10 meters. Histogram of the heights is shown here. You can see that there's nothing above 25 meters. There's a lot of 0 meters where the ground is, and there's a majority of the points are under 10 meters as expected. You can then integrate those together and get the canopy height model classification image, where we've got colors for ranges. 0 to 5 meters is the yellow. That's the majority of the imagery here. The blue imagery shows the ground. This canopy height model classification image shows much better, shows the whole thing in much higher clarity than just the canopy height model by itself. When we aggregate the points together, we get this model. So this is very much a work in progress. We've been able to analyze a couple of tiles only at this stage out of the several hundred, but we'll continue on and go as far as we can while we have the students working with us. Another point was that we need the canopy height model for canopy cover for trees, both over 2 meters high and over 3 meters high. There's some controversy as what constitutes a tree, so we'll provide canopy height cover for both 2 and 3 meters. So that's what I've been currently working on. So summary and conclusions. We registered our small company in, I think, October 2020. We started off working in Internet of Things and smart cities, but we've already moved since then into big data, and in particular into geospatial information systems type data. We've written papers, presented in conferences and journals. We're actively doing these current projects, the radix analysis and the canopy cover for local Victorian government areas. We've worked mainly with Swinburne University, and I think occasionally just once with Monash, but we're certainly open to collaboration with other universities. So thank you for that, and I might leave it up to the ask for questions on the floor. Thank you, Simona.
Thank you so much, Peter.
I might just stop sharing.
That was really interesting, and you pointed out some of the urban problems that we know a lot of cities have recently in Australia, which is the urban heat island due to, extensive level of constructions without taking into consideration the heating aspect, and this is quite an important problem to solve at the moment. So I'm so happy that you did something in this space that could be used for this analysis. All right. So before we open up to question and answers, we can just, if you agree, we can stop the recording, and we will just let the conversation do a free flow from here with everyone that is connected.